Imagine the next time Starship, the largest, most powerful flight system ever built, descends from the heavens. It doesn't aim for the chopstick arms of the Mechazilla tower. Instead, it streaks toward a solitary dot in the middle of the ocean. What happens if SpaceX decides to put this skyscraper-sized rocket back on a deck of an autonomous spaceport drone ship? At first glance, the idea of a Starship landing on legs sounds like a reversal of progress. From its inception, the vehicle was designed with no landing legs to maximize the payload-to-orbit ratio. By removing the legs, SpaceX effectively eliminates dead weight that doesn't help reach orbit, allowing for the rapid turnaround and high-mass delivery required for Mars colonization. In the brutal calculus of rocket science, every kilogram saved on hardware is an extra kilogram of cargo for the stars. However, a pragmatic problem is emerging: launch cadence. SpaceX's mission profile requires Starship to fly dozens, eventually hundreds of years. Relying solely on a single Mechazilla tower creates a catastrophic single point of failure and a logistical bottleneck. If one tower is undergoing maintenance or damage during a catch, the entire fleet is grounded. This necessitates a Plan B, a secondary recovery method. But let's be clear. A Starship landing leg is not just a scaled-up version of the Falcon 9's carbon fiber struts. 1. The physics of scale. A Falcon 9 booster weighs roughly 25 to 30 tons at landing, whereas an empty Starship upper stage is estimated at 100 to 160 tons. 2. Thermal management. These legs must survive the 1400 degrees Celsius plasma of re-entry while integrated into the ship's stainless steel hull. 3. Dynamic stability. They must possess the mechanical strength to stabilize a 50-meter tall structure on a deck that is pitching and rolling in the Atlantic swells. SpaceX isn't just building a leg. They are re-engineering the very concept of orbital recovery. Technical evidence and insights for narrative depth. 1. The 30x advantage. To ensure the legs don't melt or buckle, SpaceX likely utilizes their proprietary 30x cold-rolled stainless steel. Unlike the carbon fiber used on Falcon 9, this alloy's yield strength actually increases at cryogenic temperatures and maintains structural integrity at much higher heat thresholds. 2. The 39A precedent. Recent filings with the FAA regarding Launch Complex 39A in Florida show a massive increase in planned Starship operations, up to 44 launches per year. This regulatory data supports the bottleneck theory, as the infrastructure must support nearly weekly launches, making offshore recovery a mathematical necessity for overflow. 3. Thrust-to-weight dynamics. Landing a Starship requires 3 Raptor engines, providing nearly 840 tons of thrust. Managing that much energy on a floating platform requires a damping system far more advanced than the aluminum honeycomb crush cores used on smaller rockets. On April 21st, 2026, the legendary Autonomous Spaceport Drone Ship, ASDS, just read the instructions, completed its 156th recovery mission for the Falcon 9. While this marks a milestone for the workhorse of the SpaceX fleet, it is far from a retirement. Instead, it signals a strategic evolution, the transition from the Falcon era to the Starship era. The vessel's mission is shifting from supporting the world's most reliable rocket to anchoring the most ambitious launch system ever conceived. The center of this orbital revolution lies at the historic Launch Complex 39A in Florida. This site is set to become the headquarters for Starship operations. To accommodate this, many routine Falcon 9 missions are expected to shift to Space Launch Complex 40, allowing 39A to focus on Starship's immense requirements, including tower catches and Falcon Heavy launches. The sheer scale of the planned operations is staggering. The Federal Aviation Administration, FAA, has already authorized up to 44 Starship Super Heavy launches per year from this single site. Mathematically, this translates to 88 landing events, 44 recoveries for the Super Heavy booster, and 44 for the Starship upper stage. The operational strain of such a high cadence cannot be overstated. Starship is not merely a larger rocket, it is a different magnitude of aerospace vehicle. Calculations suggest that Starship generates roughly 10 times the acoustic pressure and environmental stress of a Falcon 9. This puts unprecedented pressure on launchpad infrastructure and the surrounding environment. As the launch schedule tightens, relying solely on a single mechanical catch tower will inevitably lead to a bottleneck in mission flow. By reintegrating drone ships into the recovery profile, SpaceX gains a vital relief valve, a secondary landing solution that protects ground infrastructure and provides the flexibility needed for high-energy or specialized orbital trajectories. Technical evidence and market context. 1. Infrastructure optimization. The shift of Falcon 9 to SLC-40 is a proven SpaceX tactic to de-risk Starship development while maintaining revenue-generating Starlink and commercial launches. 2. Acoustic and thermal loads. Starship's 33 Raptor engines on the Super Heavy booster produce approximately 17 million pounds of thrust, necessitating the water deluge systems and robust pad designs currently being refined at 39A to mitigate the 10x stress factor. 3. Regulatory support. The FAA's approval of 44 annual launches at 39A serves as a concrete proof of intent, signaling that the transition to sea-based recovery is not a theoretical choice, but a logistical requirement for high-frequency space access. Make no mistake, Starship's landing legs are not just accessories. They are a standalone engineering marvel. To understand the scale, we have to look at the math. A Falcon 9 booster, when empty, weighs approximately 25 to 30 metric tons. Starship, however, is a different beast entirely. Built from heavy-duty stainless steel, its dry mass is estimated between 100 and 160 tons. Supporting this massive stainless steel skyscraper during a precision touchdown requires a structural support system capable of absorbing kinetic energy that would literally crush any conventional landing gear. The dynamics of the landing flip maneuver are equally staggering. While the Falcon 9 safely touches down using a single Merlin 1D engine, Starship requires the combined power of 3 Raptor engines. These engines produce a collective thrust of roughly 840 tons, nearly 10 times the power of a Merlin. To counteract this immense force and ensure the ship doesn't topple on the rolling swells of the Atlantic, SpaceX is designing a 6-leg configuration. These legs must provide a massive stability footprint, with a span estimated between 15 and 18 meters, 50 to 60 feet. This wide stance is critical for lowering the center of gravity and securing the vehicle against offshore wind shear. Why not use lightweight carbon fiber like the Falcon 9? The answer lies in cryogenic material theory. At the ultra-cold temperatures of liquid methane and oxygen, traditional carbon fiber becomes brittle and prone to cracking. SpaceX has instead opted for its proprietary 30X series stainless steel alloy. 1. The strength-to-weight advantage. According to Elon Musk's design specifications, at cryogenic temperatures, the fracture toughness of this steel actually doubles compared to carbon fiber. 2. Thermal resilience. Unlike carbon composites that delaminate at high heat, stainless steel can withstand the 1400 degrees Celsius plasma of re-entry. By choosing steel for the legs, SpaceX isn't just picking a cheaper material. They are picking the only material capable of surviving the brutal cycle of deep space cold and atmospheric fire. Here are some additional arguments and theories for your reference. 1. Theory of 30X steel, proprietary alloy. SpaceX switched from carbon fiber to stainless steel in 2018. The reason is that 301/304L steel has extremely high specific strength at very low temperatures, -196 degrees Celsius, while carbon fiber requires polymer adhesive layers that are very susceptible to failure at extreme temperatures. 2. Thrust to weight. The use of 3 Raptor engines is not only for braking, but also for creating redundancy. If one engine fails, the remaining 2 still have enough thrust to adjust the landing attitude. 3. Stability footprint. In maritime engineering, for a 50-meter-tall object to stand firmly on a barge, the footprint area must be at least 1/3 of its height to counteract the overturning moment from the sea wind loads. The figure of 15 to 18 meters perfectly matches the leaked technical drawings from Starbase. When Starship slams into the upper atmosphere at hypersonic speeds, it faces a literal wall of fire. Re-entry temperatures soar above 1400 degrees Celsius, approximately 2550 degrees Fahrenheit, a point where traditional aerospace materials like carbon fiber simply decompose or lose all structural integrity. This is where SpaceX's pivot to stainless steel becomes a stroke of genius. Unlike aluminum or carbon composites, stainless steel possesses a high melting point and a unique ability to form a self-protecting chromium oxide layer. This allows the ship's primary structure to remain intact, even if the secondary thermal protection system faces localized stress. SpaceX's design for the landing legs is a masterclass in functional integration. Instead of being external, drag-inducing structures, these legs are designed to fold flush into the ship's hull. In this configuration, they don't just hide, they become an active part of the thermal protection system, or TPS. The outward-facing side of each leg is armored with the same hexagonal ceramic heat tiles used on the main fuselage. These tiles, made of high-purity silica, are designed to withstand thousands of degrees while keeping the mechanical actuators and hydraulic fluids underneath at manageable temperatures. However, this design introduces a terrifying technical risk: the blowtorch effect. In fluid dynamics, even a millimeter-wide gap in the leg seal can be fatal. During the peak heating phase, the surrounding air turns into a superheated plasma. If the legs do not lock perfectly flush, this plasma will act like a high-pressure blowtorch, leaking into the internal compartments. Within seconds, It would incinerate the delicate Raptor engine plumbing, wiring harnesses, and structural supports. This is the ultimate sink-or-swim challenge for SpaceX's mechanical engineers, achieving aerospace-grade precision on a massive, skyscraper-sized scale. Technical evidence and supporting theories. 1. Hypersonic fluid dynamics. The shock-shock interaction theory. In hypersonic flight regimes, any surface discontinuity, such as the microscopic gaps around a stowed landing leg, can trigger what aerodynamicists call shock-shock interaction. According to computational fluid dynamics models, these interactions can create localized hotspots, where temperatures spike significantly higher than the average hull temperature. If the mechanical seal of the leg isn't perfectly flush, these shock waves can funnel energy into the internal structure, leading to a catastrophic burn-through event. 2. Historical precedent. The lessons of STS-107, Columbia disaster. The most harrowing real-world evidence for this risk is the Space Shuttle Columbia disaster in 2003. Investigation boards concluded that a small breach in the reinforced carbon-carbon panels on the wing's leading edge allowed superheated plasma to penetrate the aluminum airframe. This single point of failure led to total structural disintegration during re-entry. For Starship, achieving zero-gap mechanical precision in its landing leg deployment is not just an engineering goal. It is a mandatory safety requirement to prevent a repeat of this history. 3. Materials science. Silica tile resilience. Li-900 analogy. SpaceX utilizes advanced ceramic hexagonal tiles, a refined version of the Li-900 silica tiles developed for the Space Shuttle program. These tiles are composed of 94% air by volume, providing such extreme thermal low diffusivity that you could theoretically touch the edge of a glowing red tile without being burned. By arming the exterior of the landing legs with these tiles, SpaceX creates a modular shield that protects the high-strength steel underneath from the soak-back heat that occurs during the long descent. 4. The metallurgy of the 300 series passivation layer. SpaceX's choice of 300X series stainless steel provides a unique redundant safety layer. At high temperatures, the chromium within the alloy reacts with oxygen to form a thin, transparent passivation layer of chromium oxide. While carbon fiber would simply oxidize and turn into dust at 1400 degrees Celsius, this steel alloy maintains a significant portion of its structural yield strength. The recovery of Starship demands a fundamental shift in actuation technology. On the Falcon 9, landing legs are deployed once using high-pressure helium gas. Once extended, they are locked into place and cannot be retracted without manual intervention on the ground. For Starship, this is not an option. To support rapid reusability and autonomous operations, Starship requires electric or high-pressure hydraulic actuators. These systems allow the legs to be retracted immediately after landing, enabling the ship to be repositioned or prepared for transport without a ground crew ever touching the hardware. This shift toward smart actuation is the key to turning a rocket into a true orbital ferry. How do you secure a 160-foot-tall steel skyscraper on a pitching deck in the middle of the Atlantic? Even a slight tilt in high seas could cause Starship to slide or tip, leading to a catastrophic loss. While the Octograbber robot has been a success for the Falcon 9, the sheer mass of Starship requires more aggressive stabilization theories. 1. Hydraulic pile-driving anchors. One proposed theory involves active anchoring. Upon touchdown, high-speed hydraulic spikes, similar to those used in deep-sea mining, could be driven directly into the reinforced steel deck of the drone ship. This creates an instantaneous, rigid mechanical bond that survives the most violent ocean swells. 2. Kinetic cold welding, the Blue Origin theory. Taking a page from advanced metallurgy and concepts explored by competitors like Blue Origin, SpaceX could utilize kinetic bonding. By utilizing the immense downward force of the final landing burn, the landing pads could be designed to mechanically interlock or cold weld with the deck plating. This uses the ship's own mass to create a friction lock that is virtually impossible to break until the ship is safely back at port. Technical evidence and supporting theories. 1. Actuation theory. Electrohydraulic versus pneumatic. In aerospace engineering, pneumatic systems, like Falcon 9's helium, are one and done because of the mass penalties of carrying extra gas. However, according to control systems theory, electrohydraulic actuators provide higher force density and precision. By utilizing Starship's onboard Tesla-derived battery packs, SpaceX can achieve the high torque necessary to retract a 15-ton leg against gravity, a feat impossible with the Falcon's simple pressure blowout system. 2. The center of gravity, COG, risk in maritime logistics. According to naval architecture principles, the metacentric height is crucial. Because Starship's center of gravity is much higher than a Falcon 9's, the risk of a toppling moment increases exponentially with wave height. This explains why SpaceX is moving toward active anchoring. Without a physical lock to the deck, the static friction of the landing pads is mathematically insufficient to hold a 100-ton vertical structure against a 10-degree deck roll. 3. Kinetic energy absorption, the crush core evolution. Standard landing gear uses aluminum honeycomb crush cores to absorb impact. However, for a vehicle of Starship's mass, engineers look to plastic deformation theory. The landing legs must be designed to absorb the kinetic energy of a 160-ton vehicle descending at 2 meters per second. This requires a regenerative damping system, likely hydraulic, that can dissipate millions of joules of energy without compromising the structural integrity of the ship's main thrust puck. 4. Maritime anchoring precedents. The theory of hydraulic piles is backed by existing technology in the offshore oil and gas industry. Jack-up rigs use similar high-pressure systems to stabilize massive structures on the seabed. Adapting this to a mobile drone ship platform represents a cross-industry technology transfer that would provide the deadlock security Starship needs to survive a North Atlantic storm. Despite the tactical advantages of landing legs, they come with a lethal engineering trade-off: dead weight. In aerospace terms, this is known as parasitic mass. A robust landing system, complete with heavy-duty struts, hydraulic pumps, and reinforced mounting points, is estimated to weigh between 10 to 20 metric tons. According to the Tsiolkovsky rocket equation, every kilogram of hardware added to the ship is a kilogram subtracted from the payload. For a mission to Mars or a heavy Starlink deployment, losing 20 tons of capacity could mean the difference between a profitable mission and a financial loss. This is the core reason why Elon Musk has been so hesitant to deviate from the catch method. Beyond weight, there is the issue of operational cadence. The ultimate goal for Starship is rapid reusability, launching, catching, and refueling within hours. When a ship lands on a drone ship at sea, that cycle is shattered. It must be secured, sea-fastened, and slowly transported back to port, a process that can take days or even weeks depending on weather conditions in the Atlantic or Gulf of Mexico. Sea landings turn a high-frequency ferry back into a slow-moving logistics operation. Looking ahead, SpaceX will likely adopt a dual fleet strategy. We may see a 90-10 split. 90% of the fleet will be the lean version, no legs, optimized for maximum payload, and designed to be caught by Mechazilla for near-instant turnaround. The remaining 10% will be the Spider version, equipped with specialized landing gear for deep space exploration, lunar landings, HLS, or emergency recovery missions where a catch tower isn't available. Technical evidence and supporting theories. 1. The payload penalty principle. In orbital mechanics, the mass fraction is king. For a reusable system like Starship, the dry mass, the weight of the ship itself, is already high due to the stainless steel construction and heat tiles. Adding 15+ tons for a landing system significantly reduces the delta V, velocity change, capability. This supports the theory that legs will be reserved only for missions where tower landing is physically impossible, such as the Artemis moon missions. 2. Economics of turnaround time. Based on space logistics models, the profitability of Starship depends on sortie rates. A ship that is caught at the pad can fly again in 24 hours. A ship recovered at sea requires a massive support fleet, including tugs and technicians, increasing the cost per kilogram to orbit. This economic reality cements the Mechazilla tower as the primary recovery method for the Starlink constellation. 3. The HLS, Human Landing System, precedent. The most concrete evidence for Starship with legs is the NASA Artemis contract. Since there are no launch towers on the moon, the HLS Starship must have landing legs. This proves that the technology is being developed in parallel, but will likely remain a specialized variant rather than the fleet standard. Thank you for joining me on this deep dive into the future of space exploration. At Nok Lik Studio, we strive to bring you the most accurate and captivating insights from across the universe. If you found this analysis valuable, please give us a like, share this video with fellow space enthusiasts, and subscribe to our channel. Your support is the fuel that keeps this studio reaching for the stars. Until next time, keep looking up.